All right, today's topic is parametric equations, and you were to have read section 11.5. I know that it might have taken a couple of days. I don't know what happened with my dashboard, but everything got screwed up on that, so I had to back things up a couple of days. I'm sure that brought a lot of tears on. Okay. But first, I say that you should try to put some of this stuff into your calculator, go over the examples, and this will be example number 1 was this thing: x negative 43 plus 21t and y equal 19 plus 13t. And I believe we have talked about parametric equations in the past, and what they mean is, the independent variable is t, of course. X and y both depend on t. When you plot this, an ordered pair gets plotted. T never gets plotted anywhere. The x and the y get plotted. They are both dependent variables. Both depend on the independent variable t. Okay. Now, the book showed you how this was graphed. At this point, the ship was at negative 43.19 when t was equal to 0. And it took a long, it took this path. All right, but how you graph that? And if you graphed it, if you actually did it, it's not as simple as it seems. First you got to figure out a window that's going to capture this type of thing. First of all, we can figure out where this point is, where the path intersects the x-axis. Now, that's when y is equal to 0. So when 0 is equal to 19 plus 13t, isolating that for t, we get negative 19/13. Okay. Now, if I put, that means that my window, if I want to see this point, my window has to at least include that amount for t. So let's put this into the calculator. All right, first of all, I'm going to go to mode and change to parametric mode. And then we're going to have negative 43 plus 21t and 19 plus 13t. Okay, now going to the window. Now the window gives you t min, t max. Well, I know I need at least negative 19/13. And it doesn't hurt to go past it, because if I go past there, it's just going to be off screen, So I'll go negative 2. Now, if 1 second, or 1 hour, this is kilometers per hour. I take that back. Time is, in this case, kilometers per hour. This is over an hour. If I go to the left here, another 21, that's going to be, in the negative 60s. So we'll start this window at, say, negative 75. And we might as well go to 75, just to, that's what the book sort of looked like, let's say. All right, but I forgot to put the t max on there. Well, let's figure out how long that's going to be. And again, you can guess and check this stuff, but then you can also use a little bit of analysis. Now, if this is taking 21 kilometers per hour in the x direction, it's going to take about 2 hours to get from here to here. And then if I want to get to 75, that's going to be at least 3 more hours. So that's 5 hours past t is equal to 0. At a minimum, we might as well make it 6, and we should go by, say, 0.1 hour. That'll be enough points to plot to keep it okay. Now, if I look, what about vertically? All right, well, I want to see this area down here, right around the axis. So let's say that, and by the way, I should probably make this 10. And vertically, we should say maybe negative 10. And it's going to go, if I go 6 or 7 hours past here, then we're going to be well over 100. So we'll try, like 100 here. And we'll make the y scale 10 again, and let's see what happens. Okay, and there it is. Now, and that's what we were expecting. but I got a problem for you for tonight, a homework problem, and it sort of deals with ships like this, and when you graph it, and I do require a graph, you have to figure out what the window is that's gonna give you a decent graph. Okay, enough on that one. Now there was an additional problem in there. There were a couple additional problems in there. There's the cycloid. And we've seen the cycloid before. I don't know if you guys remember the train wheel problem from way back when. We did it in the sinusoidal unit, and that was a cycloid. And I talked about the cycloid back then. And it's a classic shape actually. And the derivation of the cycloid, it went through it. Now, we usually did this together, and I had pretty decent geometry sketchpad stuff on this. And I went through the derivation with it, and oftentimes had a student up there for it. And it takes a while to do this type of stuff, and there's no sense of me trying to go through it. If you read and studied, you might have figured that out. These derivations for these type of problems are actually very difficult. And you can do them if you want, but I'm not going to require it this year because I think it's a little bit much from the distance learning model. Anyhow, the cycloid was there, and in the book covered it reasonably thoroughly. I'd have to say, you can look this stuff up online; it's all there, and all of these things. Now, if what we're getting at, and you'll see where this is going in a second. I do have a plan. Okay. Here is another parametric curve. And there are a lot of parametric curves like this. This one's called the epicycloid, and it's formed by rolling a wheel of some sort on the outside of a circle. You know, the cycloid is formed by rolling the wheel along the straight, the ground. And, you can see the examples of that. If you want to, you can look that up online too. And there are animations of it online. Like I said, I have good animations with Geometry Sketchpad, but it's not possible to do that under these circumstances. Anyhow, this is the epicycloid. Now, if I go to the Wikipedia page, which I'm on, but I'm not going to take it off of this view where we get the nice animation. Here, they give us equations for the epicycloid. And I'm doing this to show you how you can do your assignment by looking at the Wikipedia page, and you'll see what your assignment is. It's not going to be the epicycloid. This is just an example. All right, so it says x of theta, and we use t because our calculator says t. And it gives you these values, r and r. Now, if you look over here, it says r is the radius of the big circle, and capital R is, and lowercase r is the radius of the smaller circle. So in this case, we have, for this diagram, big circle radius of 3, smaller circle radius of 1. That simplifies this very nicely. Okay, so that's 3 plus 1, or 4, cosine, and it's going to be t, minus 1, we don't even have to write that in there, cosine of 3 plus 1, 4 divided by 1, or 4t. And the y happens to be identical, except we have signs. 4 sine t minus sine 4t. All right, to the grapher we go. Make sure my grapher's on screen. I'm going to move this up a little bit. Okay. Clear that off. Okay, so we have 4 cosine t minus cosine 4t. And similarly, 4 sine. All right, now we're going to need to change this window because they're talking about an angle theta. Well, that for these ones is the central angle. And if you want to do a little research on cycloids of all types, the central angle is the thing on that. And this stuff is all very well known. It's been known for a long time, and these derivations they are quite difficult. I have to say. We've done these in the past, but certainly not this year because of the situation. All right, now when we go to the window, so we're talking about a central angle. So we probably want to go 0 to 2 pi here. And pi over 24 is usually where we go with that. Okay, now, whoops, 2 pi. I'm going to put pi over 24 here. Okay, x min. Well, looking at the diagram, it's given to us. -5 over here, 5 over there, -5, 5. Well, we can't go -5, 5 because we got a square thing going here, and it's not going to work that way. So we don't want a square like this because we have a rectangular window. So let's go. I mean, we know these things from our, -9 to 9 is fine, and we'll go with 1s on that, and maybe -6 to 6. We need a rough 3 to 2 ratio. Okay, let's see what happens. Very nice. Now, if you want to make it look like that, we can put the circle in there, and that's pretty simple. A circle is probably what you'd expect. If we want a radius of 3 circle, by unit circle techniques, we have 3 cosine t and 3 sine t. Okay. All right, just to show you how these formulas work, and we could make this so that if we went with a 4 to 1 ratio on the large to the small, then we'd have 4 cusps, they're called, as it rolls around the circle. Well, that won't alter this too much, really. It's going to change this to a 5, and this, if you stay with the radius of 1 on the smaller circle, the epicycloid is really not too bad. And if I change this to 4, then we're going to have the circle consistent with the cusps, let's say. All right, let's graph, see what happens. There we go. That is called the 4-cusp epicycloid. Okay, well, the epicycloid isn't part of your assignment. The hypocycloid is. All right, back to the iPad, and here is the Wikipedia page for the hypocycloid. Now, if you look real carefully here, and hypocycloids, if you can find some animation on it, it's changing the ratios of what makes these cusps is really pretty cool. And there's some things that you can do with it that are they're interesting to watch. It's too bad we can't do the Geometry Sketchpad because it's there's some good stuff with this. But this is a shape that you may well be familiar with. In fact, I think anybody that lives in our area is definitely familiar with it. It's the Steeler logo. At least the inner parts of the 4-cusp hypocycloid is known as the asteroid. And the Steeler logo has that. Well, here's my Steeler logo. And this is your homework assignment. You have to find parametric equations of the Steeler logo. Now, I don't want to give you my parametric equations here. I'm going to cover those up. Okay, but you can get them because if you go to the Wikipedia page on hypocycloid, it tells you how to do it, much like it told you how to do the epicycloid. You don't have to invent this. But you do have to displace them a little bit. You get the hypocycloid equations are based on a circle and like a large circle and a small circle. Well, the large circle and small circle are, for each of the hypocycloids, is actually this smaller circle. So you will have to play around with this a bit in order to come up with the Steelers logo. But you can even change the colors to the proper colors, and it's an interesting thing to do. Well, that is one of the problems on the assignment is to come up with the Steelers logo. And you should be able to do it, and you have to do it with the Wikipedia equations, because in the document that I'll post for you, it says there's a link that says you can't do this in Desmos, and it says because you can go here. Well, this is here. Now these equations over here, and this is, you can go to the Desmos to see how to enter parametric equations, which you should. All you have to do is put them in a set of parentheses, and as soon as if you use the variable t and you put it in there in the parentheses, as soon as you close that second parenthesis with the comma in between it, it'll give you this domain of t down below, and you just have to make it big enough. The 10 is actually overkill because you only need 2 pi here. So, but anyhow, this, you just go to this link and Desmos gives it to you. Well, I really don't want you to do that. I want you to go to the trouble of trying to figure out how to get the Steelers logo on the calculator screen and put it on your calculator screen. And in the document, I say you got to take a screenshot of that calculator and include it with your homework. Okay. All right, that's homework problem number 1. The other homework problem is this one, and this was right out of the book. But this was from years past, and we had a more difficult assignment back in the old days when we didn't have the school at home thing going. Anyhow, it's listed there, and it's much like the problem that we started with today of a ship moving at sea. But there's another one, and their paths actually cross, but paths can cross without them running into one another. Now, this is a fairly close crossing of these two ships, but it's up to you to determine if these ships are on a collision course. All right, and so the directions are all there on the homework assignment. It has 4 parts, A, B, C, and D. You do not have to do parts C and D. If you want to, by all means. Part D is really, really hard. You can try it if you want, but it's not easy. That I will tell you. That was always a bonus question on this assignment. And there were other parts of this graded assignment. This was in lieu of a test on chapter 11. We had a graded homework assignment. Well, years back we had a take-home test, but that proved to be faulty as far as the cheating went. So we had to back off of that and allowed graded homework. And people were allowed to work together. And you guys are allowed to work together on this, too. I have no problem with that. If you want to call each other, you certainly can. Okay. We will have 2 days to do this, because each of these problems is going to take a little bit of time. And so I want to try to keep to the time limitations. I may have been a little bit excessive in my time, and if a little birdie told me this, I have to say, and I'll try to change here. And you guys should have said something to me. I would have listened to you if somebody would have brought it up. Anyhow, so you'll have 2 days to do this. If you have any questions, of course, I'm available.